Walmy mornings.
Yes. So thank you for coming on Wednesday afternoon. I'm a longer term visitor and the organizers were graciously let me give this short talk. It doesn't connect, but I wanted to share with you what happened to me this morning. I was coming down the staircase in the college where I'm staying with another conference participant, and as we were working, we had a wonderful discussion about how great yesterday afternoon's talks were, how wonderful the speakers were, how informative, interesting. And then when we got to the Porter's Lodge, he went to the cancer conference where he was going, and I came here. So it was funny. So what I want to talk to you about a little bit, I want to say a few words about data mining and the context in which it's interesting to me, to my group and my collaborators. And simple systems have a few degrees of freedom. Complicated systems have many degrees of freedom, and each one of them is supposed to do something specific. And we tend to talk about complex systems with many degrees of freedom, in which in some way order emerges from the interactions. The one short point in this transparency is that in this slide is that if you look at billiard balls as billiard balls, it's a few degrees of freedom. If you look at them as molecules, it is a lot. And so the idea is that simplicity or complexity to a large extent depends at the level at which we try to model. So we are very interested in getting coarse-grained models for complex systems. And one of the first ones that we started playing with some time ago was the standard chemotaxis problem. We already talked about this here. So what I kind of want to ask you is to not think of this as the reality, but rather think as the reality, a stochastic model that Hans Othmer had made. This is of the order of 10, 15 years ago that he made it, of a situation like this. So I'd like you to think of having 50,000 agents. Each of these 50,000 agents has two continuous internal variables that have to do with the internal state of the cell that will determine whether the flagellae will go clockwise or counterclockwise. And each one of them has 6, 0, 1 random variables that determine whether things are going to go clockwise or counterclockwise. So I'd like you again to think of as truth a model that has 50,000 or 100,000 sets of 2 continuous and 6 random integer 0, 1 variables. And if one runs a simulation of this truth, of let's say Hans Othmer's truth, one in principle knows, and at some limit one can prove it, that one can write effective continuum hydrodynamic type equations in terms of this is a one-dimensional spatial problem, so in terms of a scalar field P, which is the cell density. What is the point in this? The point in this is that the only variable that matters when we want to be predictive at this scale is the density of cells. It does not matter what is the values of the internal variables. It does not matter how many of them have clockwise flagellae or counterclockwise flagellae. Without knowing any of all of these details, it is possible to write predictive equations in terms of the cell density. Most of the work that we do, and in the context of which data mining, as I will tell you, is important, is that we are assuming that we are not smart enough to be able to derive such equations. We do have microscopic models of many interacting particles, and what we try and do is to try and come up with multi-scale computational schemes that in effect will allow us to solve these equations without writing them down. So this is then the main idea. If one had, oh, there is a big stick somewhere here, yes. So if one assumes that there exists an equation in terms of cell density, but does not know the right closures so that one can express its right-hand side, and the only thing that we have available is the 50,000 agent-based simulator, what we can do is that we can take an initial condition in density, create agent distributions that have this density, initialize them willy-nilly, some flagellae clockwise, some counterclockwise, the internal variables, whatever you want, run the detailed simulation for a short time and observe how density evolves. It's implicit in assuming that an equation closes in terms of density, that very quickly a lot of the errors that we did in initialization are going to be forgotten, and the right percent right going, the right percent left going, the right percent flagella clockwise or counterclockwise will be quickly established. So this is some sort of quick, short time approach to a slow manifold. And then after this quick initial transient, we look at how the density evolves. We estimate the time derivative of the density, and then we take an Euler step for the density. This is called coarse projective integration. It's obviously integration of the equation for the density. It is coarse because we don't have the equation for the density. We really are basing all of this in simulations at the agent-based level, and it's projective just because we estimate the time derivative and project. After we jump, we reinitialize agents that have this density, run them for a short time, estimate the time derivative, and jump. The idea is that the motion of the agents is quick, it is messy, it is stochastic, but the evolution of the density over longer time scales is smoother. So doing this short run and using this short run to estimate the time derivative of the density, that is the right-hand side of a closed equation, is accurate enough, so that in effect we integrate the equation for the density without the closure. Okay? And this is just showing, I'll show you two views of this. Here you see the, this is a simulation of, as I told you, 20 or 50,000 cells. I don't remember exactly what the number was. Here you see the evolution of the PDF of the particles. Here you see the cumulative distribution, and there is blue curves and red curves. The blue curves come from evolving the cells all the time and looking at their density. The red is you evolve them for a short time, estimate the time derivative of the density, jump the density, initialize cells that have this density and everything else bananas, let them run for a little bit, estimate the time derivative, and so on and so forth. So this is using the short simulation with a fine scale code to establish the closure on the fly. This is another view of exactly the same thing. In what I'm going to show you, I want you to remember that red dots are cells that go that way, and yellow are tumbling, and blue are going this way. And as you run this simulation, which is one of these projective simulations, I want you to notice that from time to time, the simulation kind of goes to a fine line and opens up again. This is supposed to make you see that compared to the time of the evolution to steady state, it takes a very short time initializing the cells with a given density, but all the rest of the internal and external properties bananas, you let them run for a little bit, and very quickly the quote right distribution of right going, left going, numbers of flagella, and so on and so forth is established. So the fine scale simulation over a short time establishes the right closure, if you want. I also want to tell you that this type of doing numerical analysis, not based on equations, but based on short bursts of an inner simulator, is something for which you can also do numerical analysis. So with Bill Gear, you can think of having a number of short steps of an inner integrator, use the slope, the time derivative estimated from the tail end of this, and making a big jump. You can think of this as just a straight numerical algorithm, and you can do it stability analysis, and it is very, very good for problems in which you have big gaps separation between time scales, fast initial transients, and then moving on a slow manifold. The point is that this is a set of tools that works when you can very easily go between looking at a fine scale simulation, like the detailed cells and their flagella and whatever, and observing their density. That, for let's call it restriction, having the detailed version of the problem and looking at what the coarse version is. It's also important that one has the reverse ability. That is, it should be possible to start with density and then create cells with their detailed flagella and inside states given this density. Okay? All of the simulations are done at the fine scale level, but the idea is that we can use these full simulation results observed appropriately to do some macroscopic results like prediction, steady state, and so on, and calculation. We can do it faster. The idea is that we know that, actually this is the, the basic idea is we know that an equation exists. We know at what level the system closes. We don't know exactly how it closes. It doesn't matter. We can just use the idea that it closes to do the calculations better. Now, in the example that I showed you, I have, I guess, two stages in what I want to tell you. In the example that I showed you, I pretended that I didn't know what the right closed equation was, but I pretended that I did know what the right macroscopic variable was. It was the density field, okay, from the work of a lot of other people. This is a very different example from the work of a friend, Tony Roberts, who is an Australian mathematician. This is a problem in which, so this is a random two-dimensional velocity field. The color is just to give you a feeling of how it moves around in 2 dimensions. What Tony Roberts did with friends is to look at clustering and steering in a plankton model. What he did, and this is another movie that has a fine and a coarse version. This is the fine version. He put 20,000, quote, planktons on this two-dimensional field, and then he let them go. Each one of these would do a small random walk. Each one of these would be steered by the macroscopic random field. Each one of these would give birth and die. And if you look at them, this is what the plankton are doing, and then this is what the pair correlation function of the plankton is doing. Let me play it again. The main point is the detailed simulation does all kinds of things, striations and so on and so forth, and never becomes stationary. But if you look at the evolution of the statistics have a very nice evolution to a stationary state. It looks like a nice PDE for the pair correlation function that evolves to a steady state. And no, it's an incompressible flow, and these are passive particles in this flow. The only active thing that they do is that they do a small random walk on top of that, plus they give birth and die. And when they give birth, the offspring is put just next to the father or mother, whichever way you want to think of it. But the thing that I want to say, however, is that while for the first problem it was kind of pretty obvious what the right variable was, because we're all familiar with it, should be the density field at the macro level. Here, if one just showed us a movie, it wouldn't be obvious that a good variable in which to try and close the system with would be the pair correlation function. If we don't, these are the rules. If you don't have the pair correlation function, but just somebody tells you that it is possible to write a closed equation for the evolution of the pair correlation function, then you can do the same thing I was telling you before. Run the particles for a short time, estimate the time derivative of the pair correlation function, jump the pair correlation function further in time, put down particles that have the same pair correlation function, run them for a short time, estimate the time derivative, and so on and so forth. You realize there's many, many, many ways of putting down particles that have a prescribed pair correlation function. It really doesn't matter in this problem how you put them down. As long as the macro pair correlation function has the right shape, then the evolution at the macro level looks fine. So what is again the idea? The idea is that if I have a detailed simulator, and we saw a lot of both experiments and models this week that look at a detailed complex fluid, and this is the important part. Somebody has to tell us what are the right macroscopic variables, what are the right variables in terms we would like to write macroscopic closed equations, but we don't know what the closure is. We can use the idea that a macroscopic equation exists to make the simulations smarter than just running all time, all space, and so on and so forth. There's a lot of things that I can do. I don't want to talk about it in great detail at the moment. I just want to say that it is possible to, as I said, to use the idea to do the simulations better. We call this equation free not because there are no equations. There are equations at a fine scale. It's the coarse equations that we don't have. And so now what I want to discuss, and that's the data mining part, is what is it that we do when we don't know from a lot of people's experience or from intuition or whatever what the right macroscopic variables are. So this is a very simple Visek-Sirok kind of example that comes from talking with Ian Kazan and Cy Levin in Princeton. What you have down here is 11 little stars. They're supposed to be, well, they're self-propelled particles. Think of them as fishes, if you want. There is one blue particle. The one blue particle wants to go a little bit more to the right than to the left. And if you look at how these guys evolve, you will see that they move, of course, they don't move with a constant speed, but it looks as if they kind of slip and then stick for some time, and slip and stick for some time, and then slip and stick for some time. And when they are slipping, it looks as if they seem to have the same slope, the same velocity on average. So looking at a movie like this might suggest that this looks like a bistable system. It goes between a running and a stuck situation. the thing is, if you looked at this picture, if I gave you a snapshot of this, also I must agree the way that this is plotted is not very informative because all the little stars are almost overlapping. But if you got a picture of the instantaneous positions and velocities, is it easy to figure out what the right macroscopic variable is? What should you look at to be able to tell that you're in the middle of sticking or in the middle of slipping? What's the right phase field, if you want? What's the right macro variable, the right order parameter? And so this is an excerpt from the previous movie that my postdoc Tom Fruin kind of selected to make you and me see what the right macro variable could be. You see, when the leader is at the edge of the group seems to be stuck. But when the leader, by some fluctuation, finds himself or herself in the middle of the group, then the group is running. And so by the suggestion of this little excerpt of the movie, these are again the rules, which are of the Visek-Sirok type, Thomas did a lot of processing of the movies that he saw, and he saw that every time that the leader was far away from the middle of the group was stuck. Far away, stuck, far away, stuck, far away, stuck. And every time that the leader was very close to the middle of the group was running. Very close to the middle was running. Very close to the middle was running. So you can say that by looking enough at the problem and having a lot of experience at the problem, Thomas figured out what a good order parameter was. A good order parameter was the distance of the leader from the middle of the group. So the question is how to get the computer to figure this out as opposed to Thomas. And I've always wanted to kind of so this is Princeton, and this is not the River Cam, but it's actually it's Carnegie Lake, which I think was given to Princeton by the Carnegie so that we also, our students also could draw. And my house is somewhere here, and I want to illustrate the idea of one particular algorithm for doing nonlinear manifold learning that is looking at data like the ones that I showed you and figuring out what the right variable is. So in this version of trying to think of Princeton, I'd like you to think of each snapshot of each configuration of the simulation as being a house in Princeton. And the noise makes you go from configuration, or the dynamic. So the corresponding activity here then is walking from house to house in Princeton. And the main point is that if you just thought of two houses, in general, the effort to go from one house to the other depends on what the Euclidean distance of the houses are. But as this little plot shows, these different pairs of houses, they have the same Euclidean distance, but the effort to walk from here to here is really much different than the effort to walk from here to here because you have to go to the bridge and walk around. If the houses are very close to each other, then the Euclidean distance is representative of how easy it is to go from house to house, to transition from configuration. If the Euclidean distance is bigger than a cutoff, and the cutoff in Princeton would be Lake Carnegie's width, then you don't believe the Euclidean distance is being representative. So here's the deal. In the primitive variables of the problem, so for the swarming problem in terms of positions and velocities of everybody, in this picture in terms of XY coordinates of the houses in Princeton. If two configurations are very close to each other, you believe this metric of their distance to tell you how easy it is to go from one to the other. But if the distance becomes very large, then you don't believe it. And the question is, how do you take a distance that you believe when it is small and then create a set of coordinates and a new distance that you believe both when it is small and when it is large? In this set of coordinates, that's the right variables that you would like to be able to play with or observe the problem. This is, if you Google ISOMAP, you will get a site at Stanford that talks about a very important 2000 science paper. There were two of them back to back. Here is high dimensional data, 3-dimensional, that live in low dimensional space, 2-dimensional, but not a plane, a curved manifold. And the idea is that the same thing that we were talking before, that here is a pair of points for which the Euclidean distance is equal to the Euclidean distance of this pair, but the geodesic distance of going here to here and the geodesic distance of going here to here is different. So the important thing is, how do you get the computer to discover geodesic distance, or how do you get, if you want the computer to discover that the arc length along this set of variables is the right variable to look at. Clearly, doing principal components would not work in this. The data are two-dimensional, but there is no nice two-dimensional plane that passes through them. So the standard, well-tested, sacred method of doing reduction by principal components, it will work, but it will not give you a parsimonious representation. So the basic idea, again, is that we believe Euclidean distance when it is small, because when it is small, it is close to the geodesic distance. We don't believe it when it is big. And the way that one uses this information in order to, one of the ways that one uses this information to find good variables is to take all the data points from a simulation and create a graph from them. Each of the data points is a node in the graph, and the edges of the graph have weights. These weights have a diffusion kernel, as you see. There is the Euclidean distance that we talked about, and then there is this characteristic scale that has to do with when do we believe the Euclidean distance is meaningful of the difficulty of transitioning, and when is it that we don't believe it. This is clearly something problem dependent that we have to play with. But basically you see that if two things are far enough away, then they're practically not connected. So you only count things that are close enough to each other, and if you want to find the distance between somebody and somebody very far away, you don't look at their direct connection, but you look at all possible short step paths between the two. And the way that this is done is that one creates a matrix that has in it all of these kernels, that has all the pairwise distances, and then basically with the appropriate scaling, this is a you can make a Markov matrix out of it, and then you find its eigenvalues and eigenvectors. There is one eigenvalue. So in effect, one does diffusion on a graph that comes from on data that come from the simulations of our problem. And if one is lucky, then one would find that a few of the eigenvalues of this have a gap compared to other eigenvalues. In that, it sounds similar with principal components. And then one might be able to use the components of the data along these directions in order to describe the data quite well. So if you do this matrix problem in the example that I showed you here, and then you look at each one of the points and you look at their components in the first two non-trivial eigenvectors of this matrix, then this procedure will find that the z direction is a good variable and that the arc length is a good variable. So what it will do is that it will take this ribbon and kind of open it up and tell you that there are a couple of interesting directions that parameterize all of the data that you have, and the rest, let's say, is noise. So why would eigenfunctions of diffusion have something to do with parameterizing manifolds? I kind of tried to make a little illustrative slide here. So I'd like you to think of a two-dimensional manifold that looks like a thin strip, so just a little parallelogram, and then think of having lots and lots of points sampled from this parallelogram. We kind of all know that if we calculated the eigenfunctions of the Laplacian on that domain with no flux boundary conditions, one of the eigenfunctions that we would see, one of the first ones would be like, if you think of this as the x direction and this the y, you'd get something like cosine y. So very quickly, one of the eigenfunctions you see is 1-to-1 with one of the two important directions, the x direction. If you calculate higher eigenfunctions, you will find you'll find cosine 2x, you'll find cosine 3x, but at some point you're also going to find cosine y. That is, you're going to find an eigenfunction which is 1-to-1 with a second important direction. Doing the graph Laplacian on a graph that comes from sampling here at some limit is exactly the same, or asymptotes to finding the eigenfunctions of the Laplacian in the domain. And so in the same way that cosine x and cosine y are eigenfunctions that are 1-to-1 with x and y, eigenfunctions of the graph Laplacian based on these data will find the x and y directions. They will do it even if this is not a beautiful, planar parallelepiped, but if it is something curled as we saw before. If it is something curled in high-dimensional spaces with extra noise, then again you will have a way, looking at gaps between eigenvalues, of figuring out that maybe 2 or 3 directions are enough to parameterize your data. This is just a slightly more weird domain to show you that one of the eigenfunctions has to do with the angular direction and one has to do with the radial direction which is what our brains would kind of automatically tell us. So these are the data from this little Xerox 1D with a leader model, and all of the snapshots that had to do with when they're slipping are around here, and all the snapshots that had to do with sticking are around here, and the transitions between them are along this curve. So what you see is a summary of the little movie I was showing you before, but it is now projected on the first two non-trivial eigenfunctions of this process, which is called diffusion map, starting with Belking and Yogi, and then with Rafi Koifman and a lot of his students and collaborators. And so this basically tells you that this one variable, phi2, is 1-to-1 with all of the snapshots that we saw, approximately. And so this is a ridiculously simple graph that we were very proud and happy, well, at least happy with Thomas when he did it. Every dot in this plot is a snapshot of the movie. This is Thomas's coordinate, the distance of the leader from the middle of the group, the one that comes from observing the data or knowing something about the problem. And this is the component of the data on the first non-trivial diffusion map eigenvector. And you're basically supposed to see that it is 1-to-1, which either means that Thomas is smart or that the algorithm is correct or a combination of the two. And then you're also going to see that there is some places where it is kind of more flat or more vertical or fatter. That probably would suggest that the second variable might be necessary to do something better at that place. In what way is this useful? This is a one-dimensional problem. It is a one-dimensional stochastic problem. So in principle, one can write an effective 1D SDE that models the dynamics of this slightly messy problem using as a coarse variable or as a reaction coordinate or as an order parameter the component of the data on the first non-trivial diffusion eigenvector. And then this is the corresponding potential. And then there is jumps between sticking and slipping. What's the idea? If you know what the right variable is, you can do a few short bursts of calculation with the model around, build this potential, and then use it to get long-term information from the problem. I have a bunch of other examples, but I will just kind of go to a summary slide, and I'd be happy to talk about this more. So the idea is, of course, doing data mining is interesting and important in general. We are interested in it because we want to get from the data mining the right variables with which to do our equation-free stuff. That is, we want to get these variables and use them to accelerate simulations. So there is the issue of doing data mining to get the right variables in order to get reduced models. What is easy and what is difficult? I should just say it is difficult. Like, suppose that you know what the right variables are, and the real difficult thing is that these variables have no obvious physical meaning, and they're not supposed to have an obvious physical meaning. You can work with them, you can do calculations with them, but just knowing that something has coordinate phi2 equals 0.5 does not automatically tell you in a very satisfying way that something has a bigger gradient or a bigger concentration or something. So the fact that these things, you can work with them, but they have no obvious physical meaning that you can try and get a different kind of understanding, it's a shortcoming. They can help you do calculations better, but that don't necessarily help you understand things better. So the physical meaning is a problem. Also, let's say that you want to bias your experiments. You want to collect data at these new values of the diffusion map coordinates at which you don't have data yet. In general, it is not easy to create physical realizations of your complex system that have these variables. It is not trivial, it is not impossible, but it is not easy to create physical realizations that have such observables or statistics. And so these are a couple of the things that we work on. How this lifting business, like if somebody tells you what the observables are, how do you create realizations that have these observables? And we also have some work on, if we know what these variables are, how to evolve in the space of these variables. And that's what I wanted to say. Yes.
So like, so I have a question which I think is related to what you were talking about in the very end. So, like, let's pretend that you did want to know what the coarse grain, let's say that you actually did want to know what the correct coarse grain equations were.
Okay.
Could you, like, assuming that they exist, could you kind of use related methods to basically kind of build them up?
Okay. This is the kind of thing that in most of my research I don't do, but nevertheless. So a very simple version of doing what you just said is this. If somebody knows that in this problem there's only one important reaction coordinate, then what you could do is that you would just make a grid in this coordinate, run a few simulations in each one of these places, fit, let's say, the drift and diffusivity of your SDE, and then through interpolation you have a model. How can you use this model? You can get average switching times, or you can get average velocities, and so this is a model which is fitted. How did this procedure help you? It helped you by helping you create a grid, like in how many places should I estimate so that I have a nice surface. It doesn't tell you, unfortunately, and that's a very medieval part, it doesn't tell you any explanation of what this gradient in this funny variable means. Did I answer?
Well, no. I mean, like, what I was asking more is that. So let's pretend like you didn't know that, like, that diffusion with. Let's say you knew that density was the right thing.
Yes.
But you didn't know that diffusion with drift was the right description.
Yes.
Then by running the microscopic simulations and then looking at how the density evolved, and like looking at maybe trying to do like looking at somehow partial derivatives of like that. Yeah. Like, could you kind of build up that it was diffusion and drift? Like, I mean, like, you know.
Okay. So
schematic stuff.
So I'll give you a version as I am kind of like a stream of consciousness answer. You can certainly do it, but let's say that there is 3 important physical components in the right-hand side. You can get the right-hand side, but this would not tell you that the right-hand side has one component from streaming, one component from diffusivity, and one component from whatever. So it is useful in terms of accelerating simulations, but not so nice in terms of, but since you asked, one of the things that I did want to say is that something really interesting, so I mean, clearly it is in principle interesting to say how many are the important variables. Another interesting question, which sounds trivial, but which I didn't used to think very much about, is the question, what is the right model for the right-hand side? Usually somebody gives us a model, let's say it's a PDE, and then we know how we go about integrating it, how we know about discretizing, how many boundary conditions are necessary, and so on and so forth. Here, one question is, what are the important variables? And then a second interesting question is, what is the right nature of the right-hand side equation that you want? Do you want to have an ordinary, do you want to have a deterministic right-hand side? Do you think a deterministic right-hand side would be good? Do you think that a stochastic right-hand side with white noise would be good? Or do you think a deterministic a stochastic right-hand side with jumps noise would be good? This, of course, it's a very natural question. What I think is interesting is that it leads you to the following idea. You could think of designing computational experiments to qualitatively answer these questions. Not to get necessarily a formula for the right-hand side, but you would say, what simulations would I have to do to confirm, or at least not disprove, that the right-hand side is indeed an SDE with white noise in these variables. I don't know if you see the dumb thing that I'm saying. If somebody gives you a formula, all of these things are obvious. This is an SDE with white noise. But if you have a particle simulation that is running around, it's not clear what the right variables are, and even if you have the right variables, there is a whole hierarchy of different types of models that would be in the right-hand side. And I think it is interesting to consider this simple concept. What is the design of simulations with a fine-scale model to confirm that indeed an SDE, a PDE, an integral differential equation is the right type of model with the coarse variables that we have? Is it a local model or a non-local model? Is it a white noise model or a jump noise model? This is something that we don't usually do. Usually we start with the equation.
So you showed an example where you have data on a 2D manifold in 3D.
Yes.
Well, that's not a very big
No.
system.
Oh, what are the biggest things?
Like Navier-Stokes. So, 100 dimensions and infinite. Can you use these techniques for something like that?
Well, there is two things. There's two versions in the Navier-Stokes. The first thing is Navier-Stokes are PDs and local, which means that you don't have, it's one issue as to what is the PD, but then locally, how many things do you need to know in order to be able to make a prediction for the time derivative at one point? So locally, you know that you need velocities and you need velocity gradients, but you don't need more than, you don't really need stresses.
But I'm thinking more about back to the inertial manifold problem.
Yeah.
Where do the solutions live, and can we use that information to extract information out of simulations or data?
Okay, I would say
Linear POD is what I would.
Yeah, that's also a good point. This is nonlinear. Maybe some of the people that do the corresponding mathematics would be very offended if you just said this is just nonlinear POD. But this is a nonlinear extension of the types of things that we had been doing before. And the idea is exactly the same idea as in inertial manifolds. There is a separation of time scales that allows you to forget some variables, either because they get slaved quickly or because their statistics get slaved quickly. So what we're talking about is what are the variables that parameterize the manifold that you're interested in. I will say one more thing and shut up on this, that there is one issue about what goes into the right-hand side, like how many variables are necessary for the Navier-Stokes, and it's another issue, what is the dimension of the attractor of the Navier-Stokes. These are similar but different questions. One is how many variables, and the other is how many degrees of freedom in the attractor. I promised I would shut up. Let me say one more thing, which is just personal. I thought, as a student, that the most amazing thing in the Navier-Stokes equations was having Newton's formula that said that stresses are proportional to velocity gradients. I actually think that the greatest thing is not this now. I think it's the decision that you can just stop at velocity fields, that you don't need higher things. If you know what are the important variables, you can just fit the stupid right-hand side and work with it. It's not very elegant, but so I think that deciding the number of variables in which they are is maybe more important than the right formula.
Well, we stop it for
Okay.
talk session.
Thank you.
We go on.